Hello there, and welcome to my channel, Engineering Progress, where we bring, dissect, and explain in easy-to-digest bits some of the most complex engineering feats and happenings. Today on this stream, we are discussing what the reasons are behind the cataclysmic collapse of both of the Edenville and Sanford dams. Also, please don't forget to click the subscribe button, destroy the like button, put on notifications, and drop comments below on this or any content you guys want to watch. Thanks. Throughout time, civil engineering, may more than others, is a profession that learns from failure. Therefore, when the Edenville and Sanford dams in northern Michigan failed in the late afternoon of May 19, 2020, the investigations began almost instantly. Daniel Pradle, PhD, PE, DGE, FASCE, a professor of practice in geotechnical engineering at Ohio University, headed an ASCE team examining the dams, pinpointing what went wrong and how similar disasters can be mitigated in the future. We keep having earth dam and levee failures almost every year, Pradle stated, and they're preventable. Pradle, who spoke with Civil Engineering Source about the failures and why he's concerned about the safety of thousands of other dams in the United States. Whenever you have a failure, you need to move extremely quickly because, especially for earth dams, rain washes away the evidence. One of the things that we did is we mobilized. We were there with boots on the ground within days. I think we have a very significant issue with our dams in this country. Let me give you some numbers that are in the report. Let us take Michigan alone. Michigan has about 1,000 dams. I think the exact number is 1,059. And about 270 of those are over 100 years old. The two that have failed were two of these very old dams. These were the dams that were built of earth materials before the science of earth engineering was, for all purposes, developed. Modern principles of geotechnical engineering, like compaction and stability analyses, were developed in the 1930s. So we have a large number of dams in this country that were built before the science was even available. In the ASCE infrastructure report card, they indicate that we have over 90,000 dams in the United States with a grade D for safety. I think it's important for the engineering community to be aware of this issue. Our goal was to move very quickly and make it available as a book for the community to see. According to Pradle, we use all the tools that are modernly available. We use drones that are equipped with LiDAR sensors, which gives you a really good survey of the land. They also had thermal and optical sensors. Thermal is really important because when the water gets out of the earth, it's usually colder. So by having the temperature, you can actually distinguish areas where the water is seeping out from the inside of the dam. After the material was eroded, we took samples, which gave us a really in-depth geological survey of the entire reservoir. We had the videos of the failure. We did pixel tracking analyses to see exactly how the failure progressed. We also did some in-depth analysis of the visual media that was available. Most of the time, unfortunately, we don't have the media. But here, we had people who were filming the dam as it failed. And not only that, but within a half an hour, we had video from the plane that went by. We were able to not only see the failure itself, but also the progression of the breach of the dam. This is a fantastic case history. It happened during the day, and it was available for analysis on various media thanks to Twitter and YouTube. This now brings us to the question, what really happened at Edenville and Sanford dams? To answer this, we have to firstly take a look at the weather patterns on the 18th of May, 2020. As the town housing the two dams had been receiving scattered showers for 2 days prior, before the main storm hit on the 18th. Heavy rainfall in Michigan as a whole raised the water level of Wixom Lake, an artificial reservoir impounded by Edenville Dam, higher than it had ever risen before. As the reservoir continued to rise the following day, the 19th, the dam suddenly broke, sending a surge of water downstream. As it traveled along the Tittabawassee River, the flood wave reached and quickly overpowered the Sanford Dam downstream. The catastrophic failure of the two dams impacted negatively on more than 2,500 structures and caused more than $200 million in property damage. The independent forensic investigating the event, led by Daniel Pradle, released an interim report on the failures in September 2021. The conclusions of the report includes a discussion of a relatively rare phenomenon in earthen dams. Let's take a breakdown of the investigation and try to understand what really happened. Edenville and Sanford dams were the two owned by Boyce Hydropower along the Tittabawassee River in Michigan. The dams were built in the 1920s to generate hydroelectricity. Edenville Dam was constructed just upstream of the confluence with the Tittabawassee River. It was an earth-fill embankment dam with two spillways and a powerhouse. The water held by the dam formed a reservoir called the Wixom Lake, nearly the entire perimeter of which was surrounded by waterfront homes. State Highway 30 divided the dam along a causeway, splitting the lake between the two rivers with a small bridge to allow water to flow between the two sections of the reservoir. While Sanford Dam, which is downstream, was a similar structure as Edenville, but not nearly as long. It consisted of an earthen embankment, a gated spillway, an emergency spillway, and a powerhouse for the turbines, generators, and other hydroelectric equipment. There has been a long history of disagreements between the dam owners and the regulatory agencies over both the dams, more especially Edenville Dam. Most of the dams that generate hydroelectricity in the United States are subject to oversight by the Federal Energy Regulatory Commission, or FERC. This history with the various agencies, including FERC, resulted in the revoking of the license to generate hydropower in 2018, when the owner failed to comply within particular FERC safety guidelines and regulations. Their report listed 7 concerns, but most pertinent of them was the concern that the Edenville Dam did not possess enough spillway capacity. As a result, if a severe storm were to come, the dam wouldn't be able to release enough water to prevent the reservoir level from climbing above the top of the structure, overtopping it and likely causing it to fail. After losing the license to generate hydropower, jurisdiction over the dam fell to the state of Michigan, where the disagreements about its structural condition, spillway capacity, and water levels in Wixom Lake continued. On the ill-fated day, a deluge arrived early that morning, and it didn't take long for the water levels in Wixom Lake to begin to rise. By 7 a.m., operators at the dam had started opening gates on both spillways to release some of the floodwaters downstream. Gate operations continued throughout the day as the reservoir continued rising. At 3:30 p.m., all 6 gates, 3 at each spillway, were fully opened. From then on, there was nothing more the operators could do to get the floodwater out faster, and the level in Wixom Lake kept on creeping up. That night, the lake reached the highest level in its history, only about 4 feet or 1.3 meters below the top of the earthen dam. At dawn on the 19th of May, it was already clear that Edenville Dam was struggling from the enormous forces of the flood. Operators noticed severe erosion from the quickly flowing water in the reservoir near the east spillway along the embankment. Regulators and the dam personnel met to review the damage, and a contractor was brought in to deploy erosion control measures. And the water still kept rising. By 5 p.m., Wixom Lake had risen to within about a foot or 30 centimeters from the top of the dam. As personnel worked to control the erosion problems in other places, eyewitnesses saw a new area of depression on the far eastern end of the dam. This part of the embankment hadn't been a significant point of focus during the flood because it wasn't experiencing visible erosion, but it was apparent something serious had happened. Photos from a few hours earlier didn't show anything unusual, but now, the top of the embankment sank down nearly to the reservoir level. Eyewitnesses moved to the nearby electrical substation to get a better look at this part of the dam, and within a few minutes, the embankment failed. Lynn Coleman, a Michigander and one of the eyewitnesses, caught the whole thing on camera. So what caused the catastrophic failure of both the dams? In their interim report on the event, the independent forensic team considered a broad range of potential explanations of what happened at Edenville Dam. Although the spillway for the dam was undersized per state regulations, the storm event didn't completely overwhelm the structure. The level in Wixom Lake never actually went higher than the top of the embankment, so overtopping, which is one of the most common causes of dam failure, including cascading loss of the downstream Sanford Dam, was eliminated as a possible cause of failure for Edenville Dam. The team also looked at internal erosion, a phenomenon that has resulted in many significant dam failures. Internal erosion involves water seeping through the soil and washing it away from the inside. However, This type of erosion usually happens over a longer time frame than what we witnessed at Edenville Dam. No water seepage was exiting the downstream face of the embankment, or eroding soil was evident in the time leading up to the breach, ruling this mechanism out as the main cause of failure. The cause, according to what the forensic team believes, was static liquefaction, a relatively unusual mechanism for an earthen dam. Soils can be funny because they are composed of many tiny particles. They can act like solids in some cases and liquids in others. It is worth remembering that most of our structural environment depends on the fact that soils most times act like solids, providing support to the things we build on them. How does liquefaction occur? This happens when soil experiences an applied stress, like an earthquake, that causes it to act liquid-like. And most times, it happens in cohesionless soils, those where the grains don't stick together. A great example is sand. When a body of cohesionless soil is saturated, water fills the pores between each particle. When a load is applied, the water pressure within the soil increases, and this doesn't exit fast enough. It forces the particles away from each other. The strength of a soil is obtained entirely from the friction between the interlocking grains. So when those grains no longer lap or interlock, the ground loses its strength. This has resulted in some of the most catastrophic of earthquake damages. Liquefaction normally requires cyclical loading, like during an earthquake or extreme, sudden displacement to trigger the flow. Gradual increase in loading will only cause the water within the soil to flow outward, equalizing the pore pressure. But some soils can reach a point of instability and liquefy under sustained or gradually increasing loading conditions in certain circumstances. This phenomenon is known as static liquefaction. A very good example is the difference in tensile strength between steel and glass. Both materials have linear stress-strain curves at first. In easy English, the more you push them, they push back. But both reach a point of peak strength, beyond which the soil will fail or lose its integrity. Well-compacted soil is like steel. It fails with ductile behavior. If you stress it beyond its strength, it deforms, but the strength is still there. In other words, if you want to keep deforming it, you have to keep applying a force at its peak strength. On the other hand, loose sand is like glass. If you push it beyond its peak strength, it fails with brittle behavior, suddenly losing most of its strength. The forensic team took with them various samples of the soils within and around the Edenville Dam embankment and subjected them to a stress test to see if they were liquefiable. The test showed total cataclysmic collapse, as brittle as glass would. They also reviewed construction records and photographs where no compaction equipment was noticed. The team reached an agreement that as the level of the Wixom Lake rose on the penultimate evening, it increased the hydraulic load on the embankment, putting more stress on the earthen structure than it had ever been asked to withstand. To add to this, the higher levels may have introduced water from the reservoir to permeable layers of the upper embankment, as evident by the depression that formed before the failure, increasing seepage and thus increasing the pore water pressure of saturated, uncompacted, sandy solid within the structure. Eventually, the peak strength of the embankment was surpassed, and a brittle collapse resulted, liquefying enough soil to breach a downstream section of the dam. After lacking support from the rest of the structure, the dam's upstream face collapsed a few seconds later, and all of the Wixom Lake began rushing through. In summary, with the advancement of technology through learning, we have found better ways of construction, but a lot still has to be done in regards to due diligence and obedience to laws and regulations. Let us know the next video you want us to make or your experience in the comment section down below. Don't forget to subscribe to our channel and hit the subscribe button. I hope you'll have a great day, everybody, and I'll see you all next time. Thanks for watching.